In this final section in the unit, Kinetics Part 1, we're going to discuss half-life. Half-life is defined as the time required for 1/2 of a reactant to be consumed by the reaction. This is directly tied to the way the rate of a reaction for a reactant changes over time, which is described by the rate law for that reactant. So, the half-life will also depend on the rate law and the integrated rate law for a reactant. Each rate law with its corresponding integrated rate law will have a corresponding half-life calculation. All right, so let's look at half-life first for a zero-order reaction. We know that the integrated rate law for a zero-order reaction is as follows. The concentration is equal to minus K times T plus the initial concentration. To find the half-life for a reactant, we make the following substitutions in the above equation. The concentration at time 1/2, or the half-life time, is equal to 1/2 of the initial concentration, and time is equal to the half-life time. And then we're going to solve for that half-life. All right, maybe try to make these two substitutions on your own and then rearrange to solve for the half-life. On the next slide, though, we'll go over the answer. Okay, so here's my original integrated rate law reaction. I substitute from the prior page. For concentration with respect to time, I'm substituting the concentration at the half-life. So half of the initial concentration is equal to minus K times the half-life, T1/2, plus the initial concentration. I'm going to solve for KT1/2. The way I did that was I added that to the left-hand side, so I get K times the half-life, and subtract minus 0.5 times the initial concentration. And then I just have to solve. I got to do a little bit of work here. So this is 1 times the initial concentration minus 1/2 of the initial concentration, which is just half the initial concentration. This is just combining like terms. In place of concentration 0, if you put an x here, you'd have 1x minus half x, which is just 0.5x, right? So KT1/2 is equal to 0.5 times the initial concentration. Then divide both sides by K, and we get that the half-life for a zero-order reaction is 0.5 times the initial concentration divided by K. So from the previous slide, half-life for a zero-order reaction equals 0.5 times the initial concentration over K. You should be able to derive this from the integrated rate law, which is given on the AP Chemistry reference sheet. However, it is unlikely to see a zero-order half-life problem on the exam. The half-life here depends on the initial concentration and the rate constant K. Half-life for a first-order reaction. So we start with the integrated rate law for a first-order reaction, where the natural log of concentration is equal to minus K times T plus the natural log of the initial concentration. To find the half-life for a reactant, make the following substitutions. Again, the concentration at the half-life is half of the initial concentration, and the time now is the half-life time, or just T1/2, and then we're going to solve for that. Again, maybe try to make these two substitutions on your own and solve for the half-life, but I am going to go over the answers on the next slide, and it does require a little bit more of an intermediate algebra with these logs, these natural logs and the laws for those logs. Okay, so this is just my integrated rate law for a first-order reaction. I substituted from the prior page. The concentration that I am concerned with is when I reach half of my initial concentration. So half of my initial concentration. And then that happens at the half-life, right? All right, now solve for KT1/2. So I add KT1/2 to the left. and subtract the natural log to the right. So we have the natural log of the initial concentration minus the initial natural log of half the initial concentration. Now, there is a log rule in logs that says the natural log of x times y is the natural log of x plus the natural log of y. So I can rewrite natural log of 0.5 times the initial concentration as the natural log of 0.5 plus the natural log of the initial concentration. So that's what I've done here. The next thing I did was distributed the negative sign. So now I have the natural log of the initial concentration minus the natural log of 0.5 minus the natural log of the initial concentration. Now notice these two terms, this is positive natural log of initial concentration minus natural log of initial concentration. That is 0, right? So what I'm left here with is kt1/2 is equal to negative natural log of 0.5. The natural log of 0.5 is negative 0.693. So that becomes positive 0.693. And I divide both sides by k, and I get that the half-life of a first order reaction is 0.693 divided by k. So here we see the half-life for a first order reaction, 0.693 over k. You will not be required to reproduce the derivation of this result. You will be given this formula on the AP chemistry reference sheet, and you should be familiar with it. First order half-life problems are commonly seen on the AP exam, and you should recognize here that the half-life does not depend on the initial concentration. It only depends on the rate constant K. Also, it's important to note that radioactive decay is a first-order reaction, so it follows the above half-life formula. So if you're answering a question on the AP exam related to radioactive decay, this same half-life equation applies. Finally, let's discuss half-life for a second-order reaction. The same approach is used to find the half-life for a second-order reaction, but in this case, we use a different integrated rate law. We use the integrated rate law for a second-order reaction. 1 over the concentration is equal to Kt plus 1 over the initial concentration. To find the half-life, we're going to make these same substitutions where we're looking for half of the initial concentration, and our time is just our half-life. All right, so let's make those substitutions. So here's our integrated rate law for a second order process. For concentration with respect to time, we are concerned with when the initial concentration is half, right? Half the original concentration. And that happens at what is known as the half-life. So we've substituted. Now we're going to solve for Kt. I need to subtract minus 1 over initial concentration to solve for Kt1/2 is equal to 1 over 0.5 times the initial concentration minus 1 over the initial concentration. Now, this is the same as having a half in the bottom of the fraction is the same as having a 2 in the top of the fraction. So in other words, multiply the numerator and denominator of the first term by 2. Okay, multiply the numerator and denominator of the first term, this is the first term, by 2 to get a common denominator. So we get 2 over the initial concentration minus 1 over the initial concentration. So 2 minus 1 is 1, so we're left with 1 over the initial concentration, and then divide both sides by k to solve for the half-life, and we get 1 over K times the concentration of the reactant at the beginning, or the initial concentration. Okay, so the half-life, as we derived in the previous slide, for a second order reaction is 1 over K times the initial concentration. You are not given this formula on the AP chemistry reference sheet, but you are given the integrated rate law, and the derivation is not too difficult. It is, however, unlikely to see a second order half-life problem on the exam. What you should recognize, though, is that in contrast to the half-life for a first-order reaction, the half-life for a second-order reaction does depend on the initial concentration, and that the half-life for all reactions, regardless of rate law, depends on the rate constant K.